My name is John Rockman. I am a physics and astronomy teacher at Castellea. I have been at Castellea for, oh gosh, 16 years now. And I've held a number of different roles in addition to my teaching. I was the advisor to the first robotics team for a few years. I run the summer science camp for middle school girls that we offer called I2 Camp. And as of just this past week, I am the advisor to our new National Science Bowl competition team that was founded by a couple of the girls who will be joining me in just a moment. So I want to tell you a little bit about what we're going to do this morning. We are, I would like to say that we think of the, I hope that's not for me. We like to think at Castellea, we like to think of science as a verb. So it's as much what we ask our students to do as it is anything that they'll read in a textbook. And in fact, in our ninth grade science course, we don't use a textbook. We try to set situations up where we can engage the students' curiosity as much as possible. And hopefully you'll see that in just a few minutes so that they are excited to ask questions, and then we can put them in a situation where either they're figuring out the answers for themselves, or if they really push me, I will directly answer questions sometimes. I'm going to invite our students in now. Girls, if you want to join me. Oh, hello, good morning. We've just done a lab. We've collected some data, and we're going to talk about that in a second. But before we do that, is somebody willing to share a little bit about what the purpose of the lab was? Reese, you're very excited. Go for it.
So the purpose of this lab was to determine the relationship between mass and weight on a spring scale specifically.
Okay, now I'm a little confused, Reese, because mass and weight, like they always seem like the same thing to me. Oh, Sam.
I thought so too, but they're not. Mass, it's a little confusing, but the mass of an object is essentially how much stuff is in it, and weight is actually a measure of force. So weight is how much gravity pulls on stuff in that object.
Okay, and so you were measuring the relationship between those two, and how did we do that? What did we do, Natalie?
Yeah, so what we did was we had materials of these discs. They're kind of just cylinders, and each cylinder had a predetermined mass. And we also had a scale that measured weight in newtons and a hanger to hang things onto that scale so we can measure that weight. So we just put different amounts of mass onto the scale, and then we recorded the amount of mass we put onto the scale as well as the weight the scale measured in newtons.
Right, great. So with that little bit of background, let's start. I think Sam and Reese, you guys were partners, right? Do you have data that you can share with us, or do you want me to share that?
I have my graph.
All right. Fantastic. Do you want to talk about that some?
Yeah, so this is our graph. Like Natalie said, we measured our masses in kilograms, and so we had our kilograms measures here, and then we measured our weight that showed up on the scale in newtons, and we have those here, and we put them into our data set, and we saw that they resembled a linear line, and so we added a line of best fit, and this is what we got.
And Sam, can you talk a little bit about what that, what does it mean that it's linear? Like what significance does that have?
Okay, so when data is linear, it means that it changes at a constant rate. So for example, if we had one, not that we measure this because it's really heavy, but if we had 1 kilogram, or if we had 1 kilogram disc, it would have a certain amount of weight, and then a 2 kilogram disc would increase by the same. A 2 kilogram disc would increase by a certain amount. A 3 kilogram disc would increase by that same amount. So essentially, the relationship between mass and weight, at least on the surface of the Earth, is constant.
All right. So you said a couple of things, and one of them we'll get to in a few minutes. But you were referring to a kilogram of mass, but that's a lot more than, I mean, let's talk a little bit about the range of masses you guys measured. These are pretty small, aren't they?
Yeah, we measured from 0.005 kilograms to zero point 0.2 kilograms, or 5 grams to 200 grams, and we measured it on a 2 Newton scale.
Can you give me any kind of sense, and I apologize if this is out of the blue because I don't think we talked about this, but can you give me any sense of like roughly, because I'm not really familiar with kilograms. Those are unusual units to me. Can you, like, how much is that? Like, can you give me an example of about what that's um, about, you know, something that's about that mass?
I would I would say like
Well, here's what we do know. Grams, while typically used in like if you're looking at like nutrition facts and something, it will measure different things in grams. So grams are really, really small amounts. And the reason that we use kilograms in physics, even though we were actually using a 5 gram disc and like we went measured from 5 grams to 200 grams, we actually transfer that to kilograms because, well, Mr. Rockman put it this way: kilograms are more people size. In other words, kilograms are more proportional to the like size of a human, um, versus a gram, which is really, really, really small. And a kilogram is 1,000 grams. So
Cool. Yeah, just to, you know, just to maybe give a little bit of context, I would say maybe a phone is on the order of a couple hundred grams. You know, so this 200 grams, 0.2 kilograms, that's roughly the mass of a phone, maybe a little bit more. So how can we be sure that this relationship sort of is more universal, that it extends up to those larger masses? Natalie.
well, the good news is a couple other groups used larger scales from up to I think 10 newtons. So I think they got similar data.
Yeah,
Cool. Can we see some of that? Natalie, Julie, you guys were partners too, weren't you?
Yeah, I think we were partners, but I can share our graph.
And we just measured on a 10 Newton scale, so we can measure weight on a larger range than the other group.
So this is our graph. As you can tell, it's also a linear relationship, even though we measured on a much larger scale. We used a 10 Newton scale, as Natalie mentioned, whereas Sam and Reese measured on a 2 Newton scale, but it's still very much a similar relationship.
So it's still linear. And what about the slope? Is it, I mean, is it 5 times bigger because the masses were 5 times bigger, or is there anything like that?
No, in fact, it's very, very similar. I'm not entirely sure what Sam and Reese's exact slope was, but I know that it was just under 10 newtons per kilogram.
Yeah, we got a slope of 9.81 Newtons per kilogram.
Okay, cool. And this one's 9.68. And I think, Joanne, I don't want to leave you out. I think you were also doing this, and you had different lab partners maybe. I don't remember what mass range you used, but how was your slope pretty much in line with this?
Yeah, so my partner and I, we used a 2 Newton scale, and we had a slope of 9.74 newtons per kilogram. So it's very similar to what Julie, Reese, Natalie, and Sam got.
Okay, so the fact that we have multiple groups who all did slightly different things with different ranges of mass, and we all got pretty much the same relationship or very similar relationships, gives us a lot of confidence that maybe A, we were doing something right, and B, we've maybe discovered something that's a little more universal. And I think, let's see. I don't know. I was going to share. Well, I will do this anyway. I'm going to be getting, it looks like, some messages popping up as I share this, but I think I can flick those away as soon as they come in. Some discussions about the technical difficulties we were having this morning. So what we had was all these linear relationships. I will be quick. So my handwriting is terrible. I apologize. Oh, boy, usually I take more time. Okay, and so what we saw was that it's linear. We saw the slope was about, well, let's not do that. Let's say what we had was, we had 3 different values. I think Sam and Reese, you guys had 9.81 newtons per kilogram. Natalie and Julie, you had 68?
Yeah.
68 newtons per kilogram. And we had, Joanne, you said 9.74.
Yeah.
And we had similar values throughout the class. And so we decided to take an average value of those. Does anybody remember what we came out as an average? I think Sam, you should be proud of this, I would assume.
Yeah, the average value of, I think we had like 8 groups in our class, and the average value was 9.81 newtons per kilogram, which also happened to be the slope of Reese and my graph.
Yeah, exactly. Fantastic. And it also happens to be pretty much the same value that you would find if you looked this relationship up in a textbook. And what we said then is that, what can we say? Can we say something more general? Can we say something sort of bigger picture? Joanne?
So the fact that all the groups in our class got similar slopes, and when we averaged it to 9.81 newtons per kilogram, shows that this is like a relationship between the Earth itself and some sort of gravitational force. And we see how it remains, and we speculate that it will remain constant throughout every point on the surface of the Earth. And so then what we did was we determined that it was called Earth's gravitational field.
All right, so that's kind of zooming out really quickly, right? And maybe in class this was a little bit of a longer conversation, and there were also lots of conversations about like what exactly do we write about this in our lab reports and all of that. But I want to sort of follow up what you said. It was Joanne, right? And you were telling me, you said, well, we went from, here's this relationship that we saw with all of the groups who measured this, got something similar. So we took an average value, and then we very quickly went to speculating, well, since it was the same for everybody in the room, maybe it's the same pretty much everywhere on the planet. And of course, we didn't do that. We didn't go all over the world to make this measurement. Nor did we, and I will say this with Ms. Lee on the call, who is one of our administrators, nor did we get funding for my proposed field trip to go to the surface of the moon and make this measurement there and see if our guess that maybe this is going to be different somewhere else, see if that guess was true. So we went very quickly to from what we did in class to sort of making this universal speculation. And then I think, we have a few minutes, and I think you guys had, I'm going to stop sharing at this point. I think this led to some questions that you guys had that maybe we can talk a little bit more about now as well. What were some of the questions that came up? Natalie?
Yeah, so in last class, you said something about how gravity is related to mass. And I was wondering if gravity, the strength of the gravitational force is somehow related to the size of the mass, because you said that, well, the Earth has this amount of this gravitational field, while we technically do still have a gravitational field, but it's tiny.
So what you're asking about is whether that gravitational field is related to the mass of the Earth, you mean, right? And yes, that's exactly what we talked about. And so we said yes. And so a couple of things. So first of all, if you're on the surface of, say, the moon, there will be a gravitational field that will be smaller than this. It won't be 9.8 newtons per kilogram. It's more like about 1.6 newtons per kilogram. On the surface of Mars, it's a different value. And what Natalie is asking specifically is, like, what about herself? She's mass, just like the Earth is, and just like the moon is. Does she have a gravitational field? And the answer is yes, but it's much, 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 much smaller. If we measured the gravitational field at the surface of Natalie, it would be something like 0.000001 newtons per kilogram. It would be very small. Reese?
So based on that logic, theoretically any mass has their own gravitational field. And the reason why the Earth's gravitational field is bigger than the moon's is because it's a bigger mass.
It's because it's a bigger mass, exactly. And it also has to do with the size of the planet. So it kind of has to do with mass and density because of the size question. But all else being equal, it really is kind of directly related to the mass. Joanne?
Then does Earth's gravitational field have anything to do with the fact that the Earth's moon orbits around the Earth?
It does. So so two things to say about that, and I think I'm running short on time as well. So I will end things soon because I want to give a chance for our families to ask some quick questions as well. But so two things. One is by the time you get as far away from the Earth as the moon is, that gravitational field is much weaker, but it still exists. And it's the gravitational force between the Earth and the moon that keeps the moon orbiting around the Earth. So you know, there's a couple of things to think about. Is that number one, that absolutely the Earth's gravitational field kind of extends outwards, but it gets weaker as you go farther away. Reese, real quick, and then we'll finish up.
So basically the Earth would also be revolving around the sun, and the sun's gravitational, would that work? Like the sun's gravitational field is moving the Earth and all the other planets, just like how the Earth's gravitational field is moving the moon?
That's exactly right. That is exactly right. Yes, yes. So let's see. I want to be respectful of people's time, especially since we started late. So thank you to my students for joining us this morning. Really appreciate it. Lovely to see you guys on a bright and sunny Saturday morning. And I see there's one question in the Q&A, which is there a STEM fair at Castellea? If that means, if I interpret that question correctly, you're thinking of like science fairs and, you know, like sort of student science projects, which is something that we do in the middle school science classes, but we don't do, we call it, it's sort of the big semester and like year end project for all of our middle school science classes is what we call Explo. And so that's kind of a big deal for our middle school. We don't do something similar in the upper school, although we have an enormous number of co-curricular options, such as a couple of things that I mentioned, the Science Bowl competition that Joanne and Sam are just in the process of founding. And we have a robotics team. We have these sort of high profile clubs in the upper school that we call ACE orgs, which are related to our ACE center. And a couple of them are STEM related. We have one called STEM X, where it's a student run organization that brings in speakers and other things to engage those students. How often do those ACE orgs meet? Is it every 2 weeks or so now?
They meet every week during a community time right before lunch.